Okay, I apologize in advance because this first video is going to be a lot more conceptual and vocabulary, but unfortunately we just have to cruise through it. So first is a brief review of what a line segment is. So when we talk about these things geometrically, it's a straight point bounded by 2 points. So I could have a point, a line, and a point. This could be called A and B, and this would be line segment AB. A directed line segment is a line segment that has a direction. So there's A, a starting point, and B, an ending point. It usually has an arrow on the end. Sometimes we called a directed line segment a ray. And so this is usually notated with A, B, like that. Similarly, that's going to be how we notate our vectors as well. So two directed line segments, AB and CD, are called equivalent. We don't use the word equal here, we use equivalent, and we write it with this fancy equal sign with a squiggle above it. If and only if AD and BC have a common midpoint. So basically we can think of this in terms of a parallelogram. So we know that a parallelogram has these two diagonals that share a common midpoint. So I could call this, let me do this right, A, D, B, C. So now I can say that AB is equivalent to CD and it works in the opposite direction. So we could also say that BA is equivalent to DC. And we could also do it for the other side. So we could also say that BD is equivalent to AC and vice versa in the other direction. I think you get the point. Points are collinear. We use the word collinear if they're on the same line. So if I have the points A, let me just bring that back, I guess, or I'll just do it again. A, B, C, and D. These could be connected with a line, and these could be connected with a line here. So in this case, it's a two-dimensional shape. AC is collinear, but AD is coplanar, meaning they lie on the same plane, but not on the same line. The equivalence relation that we were just talking about a couple of seconds ago works only if it has the following properties: if it's reflexive, symmetrical, and transitive. So that's where reflexive means it's itself. Symmetrical is where if it's related to another thing, then it's that other thing is also related to the original thing, meaning it works both ways. So if Katie Thompson is my sister-in-law, then I am also her sister-in-law. Like, it works both ways. Transitive is where if there's a connecting piece in the middle. So if A is related to B and B is related to C, then A must be related to C. So that's what has to apply for the equivalence relation. You have to prove all three of those things. So a vector now is a collection of equivalent directed line segments. So basically, they can be drawn a whole bunch of different ways with different starting and end points unless they're displacement vectors. So sometimes it could be here, looks like that. It could also be here. It's the same length, it has the same direction, but it could be drawn pretty much anywhere. We normally notate it with a bold lowercase letter or that lowercase letter with an arrow above it. Now, a displacement vector is a little bit more specific. It has two specific points. We know exactly where they are. We normally notate it with a bold uppercase AB or AB with an arrow over it. So A, since it's think about the direction that the arrow is going. It's the initial point, and then B is the end point or the terminal point. So A to B, the arrow points you in the direction that it's supposed to be traveling. If B is our initial point, then we do B, then A. So on that note, that would be considered an opposite vector. So that's what kind of creates negatives. So if we have B to A, then that's the same thing as the negative vector A to B. Pretty common sense. Okay, so vectors are always defined by direction and magnitude. Direction is basically the way that it's pointing. It's determined by the starting and end point, or the direction given in terms of like northeast or north. So that those lines are always parallel with one another. The magnitude is the same thing as the length. It's another word for length. The magnitude of a displacement vector will be notated with, it kind of looks like an absolute value symbol. And so for that reason, sometimes they will also do it with double bars for magnitude. Either one is acceptable, just be prepared to see both. Okay, so now into a little bit of sort of hands-on work, I guess. So now we're going to talk about, in the visual sense, addition of vectors. There are two different laws we have here, the parallelogram law and the triangle law. So the parallelogram law is what you're going to see more of on Delta Math, and the reason why is if you look at this formula here, they have a shared initial point, A and A. And then they both would meet at C. You can, with the parallelogram law, because they share that same initial point, it doesn't matter which order you add them in. So I could shift this line over and then we get to C, or you could do this line shifted up to the top and you also get C. And that's why parallelogram law works, is because the starting point is the same point. But if you'll notice in triangle law, the starting point is not the same. Instead, we make a connection at the end point of one and the initial point of another. So if I track A to B and B to C, I now know where it ends to have A to C. So that's called the triangle law. And that can be used for collinear points, meaning if I have A to B and I have B to C, then I could also call this A to C. It works if they're in a line and not just a triangle. It's just a really flat triangle. The zero vector is a vector with a magnitude of 0 and whose direction is not defined. We usually represent that with a 0 with an arrow above it, is probably the most common way you'll see it in IB, but it can also be notated with the same starting and end point, or just the number 0. Okay, as far as multiplying vectors, this one is pretty straightforward as well. You just multiply it. A scalar is just any real number, basically. A non-zero scalar k, when you multiply it, it's basically stretching it. So if k is positive, then it just gets longer. So if I have this vector here, and then I stretch it by 2, meaning I make it twice as long, it has the same direction. It's just a little bit longer. Now, if it were negative, it would move the opposite direction. So if I just had -1, it would be the same length. It would just move the different direction. So the magnitude is the product of the absolute value of k and the magnitude of the vector. So the length of this one, it's the absolute value, meaning that -1 becomes +1 because the length is still 1. The length is not negative. We can't have negative distances. We can't have negative lengths. So on that note, that's why we don't have something for subtraction, is because we don't subtract vectors, we just add negative vectors. So when we go back to what this positive section was, the opposite vectors, that's what makes it negative. So really you're just adding the opposite vector. And so I know that was a lot of vocab and a lot of information. There's a little bit of practice with triangle law on Delta Math. But the rest of this is just a starting point to make sure that you understand what we're going to hit in the next video.